Hello everyone, so today I'm going to be talking about magnetism. So I've broken this down into 5 different sections. So number 1 is magnetic flux and magnetic flux density, then electromagnetism, then generating an EMF, sine waves, and then finally motors. So magnetic flux. So an area around a magnet is called a magnetic field. The force of the magnet is represented by these lines of flux. So obviously in real life we can't see these, but on a diagram we can draw them on. These lines travel from north to south, so as you can see here, travel in rings, and they always formed closed loops. So on this diagram we can see that these loops are complete, travelling from north to south. But obviously these ones here are not complete, but that's simply because on the diagram it just doesn't show that they don't go all the way around like that. So they do form closed loops. So this is a bar magnet, and you can see how the lines of flux work here. And then this is our horseshoe magnet, and you can see how these lines of flux work here. And obviously these lines of flux are where the magnetic field can be felt. The more lines of flux there are, the stronger the magnet. Here we can see the lines of flux travelling between two magnets and two attracting magnets. So you can see that they are travelling from north to south between these two magnets, but still travelling north to south within their own magnet as well. And here you can see two like magnets repelling each other and how these lines of flux interact with each other. So the unit for magnetic flux is Weber, which WB for short, and which is represented by the Greek letter phi, which is this circle with a line going through it here. So that was magnetic flux, and now we're going to move on to magnetic flux density. So as the name suggests, it's basically the number of lines of flux, the density, how closely packed they are. So the closer the lines of magnetic flux, the greater the effects of the magnetic field. So the symbol for flux density is B, which is measured in Teslas. And here we've got the equation for calculating magnetic flux density. So the equation is B equals phi times A. So B, which is our magnetic flux, which is measured in Teslas, is equal to the magnetic flux times the area in meters squared. Okay then, so we've got a couple of questions here so we can go through. So just to answer these questions, to put this equation into some real use, if we have a magnet with a magnetic flux of 25 Weber in an area of 2 meters squared, what is the magnetic flux density? So first let's just highlight these different sections. So we've got Weber is our 25. Let's just change that for something we can actually see through. Okay. We've got, and our area is 2. So let's just write out our calculation. So write it out with the proper pen. B equals phi times the area, and that's B equals 25 Weber times the area, which is 2 meters squared. B equals 50 Teslas. And remember, it's a capital T for Teslas. So magnetic flux density, which is represented by B, is measured in Teslas. So we'll go through one more example, or if you prefer, you can stop the video here and then work this out on your own and then check your answers after that. So just to go through this again then. So if we have a magnet with a magnetic flux of 215 Webers, in an area of 3.5 meters squared, what is the magnetic flux density? So always write out the equation. It's good to get you practicing that. So B equals phi times A, which is our area. B equals 215 Weber times 3.5 meters squared. B equals 752.5 Teslas. So hopefully if you did stop the video, you got the same answer as me. Okay then, so that is the equation for calculating magnetic flux density. And the higher the magnetic flux density, the higher the number in Teslas, the greater the effects of the magnet are going to be. So now we are going to move on to electromagnetism. So when we have a circuit and when current passes through a conductor, it creates its own magnetic field. So here on this diagram we can see that it forms concentric circles around the conductor as the current passes through it. So there's a few ways we can increase the effect of this magnetic field, so increase how strong this magnetic field is going to be. So we can increase the current. Now you can do that in two ways. You can either increase the voltage, because as the voltage increases, so does the current, or you could decrease resistance, because resistance works in opposition to current flow. So if we can decrease that, we will increase the current. So that wants to go up, or that wants to go down. So increase the current by either increasing the voltage or decreasing the resistance. We could wrap the conductor into a coil, as we can see in this diagram here, because as we do that, it creates much more of a intense magnetic field. Or you can insert a magnetic core inside this coil, which further increases the magnetic field. I'll put a link to a YouTube video which demonstrates this much better. So, just before we move away from electromagnetism, there's just a few things we need to cover. So, when we see this on diagrams and drawings, we need to know, just by looking at it, which way the current is flowing and what that represents. So here we've got two diagrams. This one, so we're imagining that we are looking at the conductor end on. This conductor here has got the current flowing away from us, and that is represented by this cross going through the conductor. So when the current is flowing away from us, the magnetic field is flowing clockwise. Here, again we're looking at the same cable with the end on, but now the current is flowing towards, so we've just represented by a little dot in the middle, and here the current is flowing anti-clockwise or counterclockwise. So this symbol here, current flowing away, this symbol here, current flowing towards, and with the current flowing away, the magnetic field moves clockwise, with the current flowing towards, anti-clockwise. And here we can see the magnetic flux lines and how they interact with conductors with different current directions. So here one's moving away, one's moving towards, and we can see how these magnetic flux lines are interacting. And here we've got of the same direction and how they interact with each other. This diagram here is just a representation of a coil assembler that we've got here. And we can see the magnetic flux lines and see how intense these are inside the coil. So if you're ever struggling to remember which way the magnetic field is turning, you can use the left-hand rule of electromagnetism. So your thumb represents the direction of current flow, and your fingers that wrap around represent the direction of the magnetic field. So you might want to stop that and just give that a try and just double check that you understand that. So then, just to recap, magnetic flux is measured in Webers, WB, which is represented by phi, which is this Greek letter here, circle with a line through it. And magnetic flux is the lines of magnetic field. The symbol for flux density is B, which is beta, and is measured in Teslas, which is a capital T. Flux density is the amount of the lines of flux. And the equation for flux density is B equals phi times A. B is obviously our magnetic flux density that we're trying to calculate. Phi is the magnetic flux in Webers. A is area in meters squared. And as current creates a magnetic field in a conductor and around the conductor, we can increase the current by we can increase the field. So as we increase the current, we increase the field, and that can be done by decreasing resistance or increasing voltage. Wrap the conductor in a coil, or insert a magnetic core into the coil to increase it. And then finally we have these last two diagrams. So the cross represents the current flowing away, with the dot representing flowing towards. Right then, now we're going to move on to generating an EMF. So just one basic principle, and then I'll just explain how basic electric generation works. So one basic principle is, if we have a conductor with no current passing through it, so it's just a copper wire, and we pass that conductor through a magnetic field, so north to south, EMF, so electromotive force, which is voltage, will be induced in that conductor. So that means it will be an EMF will take place in that conductor. So if we just take a copper wire with nothing, it's not attached to any voltage, any current, anything like that, and we pass it through this magnetic field, an EMF will be induced in that conductor. So while we're still got that in his heads, I'll just talk about basic electrical generation. So here we've got our traditional coal-fired power station, which is slowly being phased out. In short, to generate electricity, what we do is we need a fuel source, so in this case it is coal. We burn that fuel source. Over it we pass cold water, which then heats up and turns to steam. This steam goes into our turbine, and the steam turns the turbine. The turbine is attached to our electrical generator, and inside there we have magnets and conductors. The turbine is attached to the conductors and spins the conductors within these magnetic fields, and as it's spinning, it is then inducing our EMF within these conductors. This EMF is then transmitted through the national grid to our houses and buildings and stuff like that. So that's the more traditional way of doing it. However, the more modern and much cleaner way of doing it is using renewable energy sources. In this circumstance, I've got a picture of a hydroelectric dam. And basically what we've got the water that's being stored by the dam here, passes through an assembly which goes through a turbine and turns that turbine. The turbine is then attached to a generator, and everything happens in much the same way as we do here. So basically, as long as we've got something that could turn a turbine, which is attached to a generator, we can create electricity. So this can either be from fossil fuels or renewable energy sources. But as long as we've got that turning motion of that turbine, we can create that electricity. So, how much EMF is produced depends on three factors: the speed of the conductor passing through that magnetic field, the length of the conductor within that magnetic field, and the angle of the conductor within that magnetic field. So, just to demonstrate it, a bit more pictures about it might make a bit more sense. So, like I said, we've got our three factors which vary how much EMF we're going to make. So, the speed of the conductor first. So, the faster it goes through, the better. The slower, we're going to create less. the length of the conductor in the lines of flux. So on these two diagrams here, I'll just draw on, we've got our lines of flux going north to south. So obviously on this assembly here, we can see that there's not many lines of flux here. So we've got this conductor travelling through here, and there's not many lines of flux, so we're not going to generate much. But here, we've got larger magnets, so the same length of cable is getting induced more voltage into that conductor. So you can either increase the size of the magnets or increase the amount of conductor within that magnetic field. So we're not going to get much there, but we are going to get more there. And then finally, we've got the angle of which the conductor is in the magnetic field. So the optimum angle to induce an EMF in a conductor is 90 degrees. So this conductor wants to break those lines of flux as it passes through them at 90 degrees. At that point, that will be the most possible induced EMF we can have in that conductor. So we want 90 degrees. If it's less, it's just not going to produce much. It will still induce more EMF, but just not as much. So 45 degrees is not good. Obviously 90 degrees is optimum. So to ensure we produce more EMF, we want it to go faster, we want more of it to be in the magnetic field, and we want it to be at 90 degrees. So there is a calculation that we need to that we can use to calculate how much EMF is going to be produced inside our generator. So what we've got here then, we've got our equation, which is E, which stands for induced EMF in volts, equals B, which is magnetic flux density in Teslas, times L, which is length of the conductor in meters, times V, which is velocity of conductor in meters per second. So E equals BLV. So then, let's just write this out then. Write the entire equation out. So E equals BLV. So E, which is obviously what we're trying to calculate, induced EMF in volts, and then let's go through it. So B is going to be our magnetic flux density in Teslas. L is going to be our length in meters, and V is going to be our velocity, meters per second. So then it's 100 Teslas times 0.5 meters times 10 meters per second. And then we just times all those together, and that will give us 500 volts. Okay then, so let's do the same with the next one. So obviously if you want to stop the video now, answer this question, and then restart the video to make sure you've got the right answer. Okay then, so let's just label everything up then. So we've got our Teslas here is 55, our length, which is 0.5, and our velocity, which is 12 meters per second. So let's work out this calculation. E equals BLV. E equals, so our Teslas is 55 times our length, which is 0.5 meters, times our velocity, which is 12 meters per second. And then E will equal, and hopefully we've all got this right, 330 volts. Okay, so that is the equation for calculating induced EMF in a conductor. E equals B times L times V. So, while we're still on generating an EMF, there's just a few facts that we're going to go through. So, fact number one. When a conductor passes through a magnet, a magnetic field, an EMF is produced. Fact number 2, EMF creates current flow. Fact number 3, current flow creates a magnetic field around a conductor. So what we've got here is, we've got a very simple diagram of inside an electrical generator. So our electrical generator is here. So this is the assembly. So round about here we've got our turbine, which is spinning away. And attached to that is our generator. So as that's spinning, it is attached to this coil assembly here. Then what happens is, because this is spinning, and we've got our lines of flux here, because we've got our north to south magnet, as it goes up and it cuts those lines of flux, it's going to induce our EMF into this coil assembly. Now remember, when an EMF is produced, when a voltage is produced, then we have current flow. Because an EMF, a voltage, is the pushing force of the circuit. So without an EMF, there's not going to be any free electrons moving. So there'll be no current flow. So now that we are cutting these lines of flux, we are inducing an EMF into that coil assembly, which is pushing those free electrons along and creating our current flow. So as this is spinning around, it's creating current flow inside, which in turn creates a magnetic field around the conductors. So that magnetic field now is interacting with this magnetic field, and then as you can see here, it starts to push and pull and attract and repel away from here. So what actually happens is, it's turning away here, the turbine's turning away, attached to the generator, the EMF is produced, the current is then formed by the free electrons moving, then we create a magnetic field around the conductor, and then it helps to continue to spin this entire assembly by attracting and repelling it. Okay. Here we have Fleming's right-hand rule, and this is only used for electric generators. So the thumb represents the motion of the conductor. So which way it's going up, is it going up or is it going down? The first finger, which is this one, represents the direction of the field, which is always north to south. And the second finger represents the direction of the induced current. So we use Fleming's right-hand rule to determine which direction current flow is being induced. So what you'd need to do first is, obviously if you get this as a question, it would be, right, the magnetic field line is travelling from north to south away from you, the force of the conductor is travelling downwards, which direction is current flowing? So it's worth giving that a try. And remember, this is only used for electrical generators, Fleming's right-hand rule. So just to recap that. A generator is a device that turns mechanical motion into electrical energy. So that spinning motion of that turbine is attached to a generator, which creates our electricity. And inside our generator we've got a conductor placed between two attracting magnets, and it induces EMF by that spinning around and breaking those lines of flux. We can induce more EMF by moving the conductor faster between the magnets, a longer length of conductor within the magnets or larger magnets, and make sure the conductor cuts the lines of flux at 90 degrees. And the equation for calculating induced EMF in our conductor is E equals B times L times V. So B, as we should know, is magnetic flux density in Teslas, L is length in meters, V is velocity in meters per second. And we have Fleming's right-hand rule, which shows us the direction of induced current flow. Next, we are just going to move on to our sine wave. Now, a sine wave is a visual representation of electricity generated at a generator. So what we've got here then, to try and explain it, let's imagine that we have got our conductor here. and then within our magnet, so we're saying that this conductor is here, and then it's within a magnetic field. So we've got a north magnet there, and a south magnet there. And in between those, we've got lines of magnetic flux, going the other way, going from north to south, like so. Okay, so I'll just get rid of those because it'll make it complicated. So we've got those lines of magnetic flux. As we begin to turn this conductor, because it's attached to the generator, not the generator, the other word that I've forgotten. So as it begins to turn, what happens is this conductor will then move. But because it started to move, it started to cut some of these lines of flux. So what we do is we plot this on a graph. So then that will go along to there. So as it's being cut at 30 degrees, we're saying, right, it's inducing this amount of voltage. As it continues to travel, it's now inducing that amount of voltage. So whatever it might be. When it gets to the top at 90 degrees, it's achieved the maximum number of cuts. So it's now travelled all the way from there. So it's now done the maximum number of cuts, which is that 90 degrees that we want. So then we have reached our maximum voltage. Now our maximum voltage, another term for it is our peak voltage. So when we've got that 90 degrees, it's our peak voltage. Obviously what happens, this will continue to spin around, and as it continues to spin around, it will continue to get plotted on this graph. So when we're at 120 degrees, we're going down, and so on and so forth. When we're at 180 degrees, we are in line with the lines of flux now, so we're not going to be generating anything. And then this continues on this half of the sine wave, which is our negative side. And so on and so forth, like so. So then, that's how the sine wave works. So we've got, this is our positive half of the sine wave, and this is our negative half of the sine wave. And the peak value we only ever take on the positive half. Also what we've got is another term that we need to be aware of, is instantaneous voltage. So theoretically, if we could stop time and stop this energy production, this voltage generation, sorry, we would take an instantaneous voltage. We would basically see where this conductor is in this spinning assembly and say, right, at that point the voltage is that. And we obviously could do this multiple times. We would just say, right, at this point in time the voltage is that. Okay then. So a few more terms we need to be aware of when we're talking about sine waves is what is one period, so, or periodic time. So periodic time is equal to 1 over f. F is equal to the frequency of the full revolution in seconds. Frequency is measured in hertz, and the frequency in the UK is 50 hertz. So basically one full revolution is, as it goes up, back down to 0, and back again. That is one full revolution. So it's basically how many times that happens per second. So in the UK, the frequency is 50 hertz. So that means this happens, the voltage goes up and down, 50 times per second. Now the reason that we don't experience this lights flickering is because this is happening so fast that there's never any interruption in voltage or current, so we never notice it. So a few calculations we need to be aware of is the average voltage, which basically splits the sine wave into 6 equal parts, and then we just do the average of that. So split it 6 equal parts and then divide it by 6. However, there's a nice little handy calculation, because that one's quite long, which is the voltage average is equal to 0.636 times the voltage peak. So the voltage peak will be its highest numerical voltage that we've got. So if we just do this, so VAV equals 0.636 times V peak. VAV equals 0.636 times the V peak, and the V peak on this one is 90 volts. VAV is equal to 57.24 volts. So that's the average voltage, but we don't tend to actually use that calculation much because it's not accurate enough. The reason it's not accurate enough is because even though we're splitting this sine wave into 6 equal parts, the voltage doesn't increase and decrease at the same rate in these equal parts. So here we can see it's travelling quite quickly up there. Same, travelling quickly up there, the voltage is increasing at relatively the same rate, but now because it's curving, it's starting to slow down. And here at the top, it's obviously slowed down enough to reduce back down. So taking an average does not always give us the most accurate reading of that voltage. So what we've got instead is we've got the root mean squared value, which does give us a much more accurate representation. So the root mean squared value of voltage is equivalent to the same value numerically as a DC voltage. So when we take our voltage readings with our voltmeters, this is the reading we're getting. So calculation for this then, VRMS equals 0.707 times the V peak. There is a calculation where it's all the 6 component parts divided, square rooted by itself. However, I find it easy just to remember these numbers. So VRMS equals 0.707 times the V peak, which is 0.707 times the V peak, which is 90, because we're on the same sine wave. And then that is equal to 63.63 volts. So even though it's the same sine wave and the same V peak number, we've actually got more voltage here because of the way that the calculation is done. Okay then, so there's 2 questions here. So if you want to stop the video and just do these questions and then restart the video when you're ready. So then for the average voltage then, we're just going to work it out of this sine wave. So VAV, which stands for voltage average, equals 0.636 times the V peak. VAV equals 0.636 times 95. VAV equals 60.42 volts. Okay then, so hopefully you got that right. And then for the root mean squared value, VRMS, so voltage root mean squared, equals 0.707 times V peak. VRMS equals 0.707 times 95 volts. VRMS is equal to 67.17 volts. Excellent. Hopefully you got both of those right. So just to recap this then. So a sine wave is a visual representation of the voltage produced in a generator. We have got our average voltage and our root mean squared voltage and the calculations that go with them, so you need to remember those. Our peak value, which is the absolute top of the value generated on the positive cycle. Our instantaneous voltage, which is just us taking a reading at any given moment. and the frequency, which is the amount of times it completes a full cycle every second, and this is measured in hertz. Okay then, the last topic we're going to look at is motors. So a motor in effect is the exact opposite of a generator. So a generator turns mechanical motion into electrical energy. A motor turns electrical energy into mechanical motion. So we've got a few examples here. We've got a motor itself and a drill, which is like a miniaturized motor in effect. So we'll just go through these facts. So fact number 1, EMF creates current flow. Fact number 2, current flow creates a magnetic field around a conductor. Fact number 3, interacting magnetic fields will create motion. So if we break these all down into our drill, for example, so EMF will create current flow. In this example, our EMF is going to come from our battery. Current flow will create a magnetic field around a conductor, which we already know, and then these interactive fields will interact with each other. So what happens is, we've got the sort of same assembly, but it's connected different, and different things are going to happen. So we have got, down here, we have got our power supply running into here. Our voltage goes through here, creates a current flow, and because it's in between two magnets in this coil assembly, it's going to create a magnetic field around this conductor. And because it's inside this north and south magnetic field, these two interacting magnetic fields are going to interact with each other and then going to create motion. So what will happen is they will attract and repel, and this will start spinning as a effect of the current being induced in this conductor. As that starts spinning, we have got our drill mechanism or our motor attached to that, which then creates our turning motion. So current goes in, creates a magnetic field within the conductor, which interacts with the magnetic field that it's already in, creates a turning motion in this assembly, which is then attached to the turning mechanism that we need to do. And we have got a calculation to determine the amount of force that is produced by this setup. So we can calculate the magnitude of this force by this equation. F equals B times I times L, or F equals Bill. So F is the force on the conductor in newtons, B is magnetic flux density, I is the current, and L is the length of the conductor in meters. So then, let's just write the equation out. So F equals B I L. So let's just break this down with this. So our magnetic flux density is in Teslas. Our current is in amps. And our length is in meters, 2 meters. So let's do this equation then. Oops. So F equals 100 Teslas times 2 amp times 2 meters. F will then equal 400 newtons. So then, hopefully that made sense. If you want to stop the video now and have a go at this one, and then restart it when you're ready. So then, let's go through this equation. F equals B I L. So then let's highlight our units. So we've got B, which is our 50 Teslas. Oops. Is that the right way? Current, which is our 2.5 amps. And then our length, which is our 1.5. So F equals 50 Teslas times 2.5 amps times 1.5 meters. And we just times all those together to calculate the force on this conductor, which would be 187.5 newtons rounded up. Okay then, so hopefully you got that right. So just to recap then, a motor is a device that turns electrical energy into motion. Current is passed through a conductor between two attracting magnets. The opposing magnetic fields create a turning motion. The equation for calculating the force produced by the motor is F equals Bill. So F equals B times I times L. B is the magnetic flux density, I is the current, L is the length in meters. And also, and I did actually forget this, we can use Fleming's left-hand rule to determine which way the force of the force of the motion is going to occur. So the same as before, but this time we're just using our left hand. The first finger is used to determine the magnetic field lines between north and south. The second finger is to determine the direction of current, and then you just stick out your thumb once you've got those 2 points to determine the direction of force. So, like I said, we've got Fleming's right-hand rules, which shows us the direction of force, the direction of the motion. Okay then, hopefully that's helped. Thanks a lot.